Hello students, welcome to the physics class of class 12. Today we start the new chapter electrostatic potential and capacitance. Our first topic is electric potential difference. The potential difference between 2 points in an electric field may be defined as the amount of work done in moving a unit positive charge from one point to the other against the electrostatic force. In the diagram, we see we have taken a source charge Q at the point O. We have to move a test charge Q0 from point A to point B. We consider a point charge plus Q located at the point O. When a test charge Q0 is moved from A to B, a work WAB has to be done in moving against the repulsive force exerted by the charge plus Q. Then the potential difference between points A and B is given by V equal to VB minus VA equal to WAB by Q0. Potential difference is a scalar quantity. Next topic, electric potential. The electric potential at a point in an electric field is the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic forces. Electric potential equal to work done by charge. SI unit of electric potential is volt. Equation of electric potential due to a point charge. Consider a positive point charge Q placed at the origin O. We wish to calculate its electric potential at a point P at a distance r from it, as shown in figure. Here in the diagram we see we have taken a charge plus Q at the origin O. We have to move a test charge Q0 from infinity to the point P at a distance r from the origin O. For that we have taken a arbitrary point A and B and we have calculated the small work done due to displacement dx. Suppose a test charge Q0 is placed at point A at a distance x from O. By Coulomb's law, electrostatic force acting on the charge Q0 is F equal to 1 by 4 pi epsilon 0 Q0 by x square. The force F vector acts away from the charge Q. Small work done in moving the test charge Q0 from A to B through small displacement dx vector against the electrostatic force is dw equal to f dot dx equal to fd cos 180 degree equal to minus fd. We know cos 180 degree equal to minus 1. That's why it is minus f dx. The total work done in moving the charge Q0 from infinity to the point P will be W equal to integration of dw equal to minus integration infinity to r f dx equal to minus integration infinity to r 1 by 4 pi epsilon 0 q0 by x square into dx. As 1 by 4 pi epsilon 0 q0 is constant, it will be out of integration. So here like this, integration infinity to r x to the power minus 2 dx. We know the integration is minus 1 by x infinity to r. That's why finally we get w equal to 1 by 4 pi epsilon 0 q0 by r. Hence the work done in moving a unit test charge from infinity to the point P, or the electric potential at point P, is V equal to W by Q0. That means V equal to 1 by 4 pi epsilon 0 Q by R. The next topic is graphs showing the variations of electrostatic potential V and electrostatic field E with distance R from a charge Q. Here in the diagram we see we have taken along the horizontal axis distance R and along the vertical axis potential and electric field. The red line showing the variation of electric potential with distance r and the black line indicates the variation of electric field with distance r. We know V is proportional to 1 by r and E is proportional to 1 by r square. That's why the graph will be like this. Electric potential at an axis point of a dipole. Consider an electric dipole consisting of two point charge minus q and plus q and separated by a distance 2a. Let P be a point on the axis of the dipole at a distance r from its center O. In the diagram, we see two charge minus q and plus q at the point A and B. O is the midpoint, so the distance between A and B is A plus A, 2A. O is the center of the dipole. We have to calculate electric potential at the point P, which is at a distance r from the center O of the dipole. Electric potential at point P due to the dipole is V equal to V1 plus V2. V1 for the negative charge and V2 for the positive charge. So V1 equal to 1 by 4 pi epsilon 0 minus Q by AP, and V2 is 1 by 4 pi epsilon 0 Q by BP. This clearly AP equal to R plus A and BP equal to R minus A. Here we have taken common Q by 4 pi epsilon 0 1 by R minus A minus 1 by R plus A. We did the subtraction of the fraction like this, and finally we get V equal to Q into 2A by 4 pi epsilon 0 R square minus A square. Q into 2A is the dipole moment P. That's why V equal to P by 4 pi epsilon 0 R square minus A square. So for a short dipole where A square is very less than R square, we get V equal to 1 by 4 pi epsilon 0 P by R square. This is the electric potential due to an electric dipole on the axis point. Now, electric potential at an equatorial point of a dipole. Consider an electric dipole consisting of charges minus q and plus q and separated by a distance 2a. Let P be a point on the perpendicular bisector of the dipole at a distance r from its center O. Electric potential at point P due to the dipole is, so V equal to V1 plus V2. V1 is for the negative charge and V2 is for the positive charge. V1 equal to 1 by 4 pi epsilon 0 minus Q by AP, and V2 equal to 1 by 4 pi epsilon 0 Q by BP. Now AP and BP have the same magnitude, that is root over of R square plus A square. So these two quantity have same magnitude but opposite sign, that's why they will cancel out and the potential is 0. So on the equatorial line of an electric dipole, electric potential is 0. Thank you for today.